Hey everybody, welcome back. So in statistics, we're always trying to find out about the population. We usually don't have access to the population, or it's too costly to get access to the population. And so we're going to have to deal with a sample. And one thing that's really underappreciated by people is the fact that a sample average, especially if you draw it at random, you take like a simple random sample, simple sample, is that since you took a random sample, anything you get out of that sample is also a random thing. It's going to be a random variable. And random variables have a probability distribution. We can talk about their expected value, about their mean and their standard deviation. And this might seem like overkill, right? We finally took a sample, and now you want to talk about its probability distribution and its mean and variance and stuff. Why would we do that? Well, the idea is that we don't know about the population. And so we're trying to figure out what the relationship is between this random variable that we've calculated from a small sample and the true population. And the relationship between these two things is probabilistic. We'd like to make, test hypotheses or make claims about the population. And that's going to have to be informed by the random nature of the thing we're dealing with. So we'll be able to say things like, well, we're pretty sure that average income in the United States is $30,000 a year. But as statisticians, we'd like to be even more precise. Rather than saying we're pretty sure, we'd like to say things like, we're 95% certain that average income in the US is between this amount and that amount. And so we're going to have to really get comfortable with applying the laws of probability to sample averages. So let's dive right in and see how this works. So we've got some population. Let's call that population X. And it's going to have its own probability distribution. Now let's just, for the sake of simplicity, presume that it's a normally distributed variable. So it's got the classic bell-shaped curve, and it's got a mean of mu and a standard deviation of sigma. Right? And this is the distribution of x's. Maybe this is every single person in the United States and their income. And we don't quite know what the average income is in the United States. We don't know this mu, but we'd like to estimate it. So what do? You take a random sample. So in other words, out of this guy here, you draw a sample of, let's say, 20 people. And you ask them what their income is, and you get a particular sample average, right? X bar. Now that's going to be our best guess for what mu is. Right? And that's usually where people stop. They just say, well, this is my best guess of this guy, and let's get on with life. But we need to be more precise about how accurate is this number, and why is it that we can feel like we can get away with using X bar as an estimate for mu. Here's the thing, is that if we had taken, we took this particular estimate of 20 people and we got a particular estimate, let's call this X bar 1, that estimate of mu. But if we had taken a different 20 people, we would get a different sample average. And if we'd taken, if I asked a third person, to go out into the world and collect a sample of 20 people, that person would have his own estimate of mu. And so really, there's almost an infinite number of different ways that we could send out researchers out into the world, and they would each calculate their own sample average. Now in practice, we would only do this once, but I'd like to consider what's the probability that we would have taken any one of these different random samples, right? And gotten each of these 4 different, or any of an infinite number of different sample averages. So I'd like for us to be able to go from thinking about the distribution of the underlying population the individuals in the underlying population, so the distribution of X, to thinking about the distribution of all of these terms that come from X, the distribution of X bars. Now this is going to have its own probability distribution. It's going to have its own mean and its own standard deviation. And what I'd like to do is explore the relationship between this parent population of X's and this distribution of sample averages. So I went into my statistical software and I ran a simulation, and I'd like to talk you through some of the results. So here I've got the distribution of income in the United States. This is my parent distribution. Now I've created this data set myself so that it's got like a nice shape and a nice and clean means. It's not like decimals and all kinds of weird numbers, but it's got a mean of 30,000 and a standard deviation of 5, and it's also normally distributed. And that's kind of a best case scenario when your population is normally distributed. Now what I did is I collected a small sample out of this guy here, and then I did it again, and I did it again, and I did it again. In fact, I did it about 100,000 times, and then I plotted the distribution of all of the sample averages. And I get this distribution of X bars. Now, one thing I'd like you to notice is that the distribution of this second distribution, the distribution of sample averages, is centered right over the same number. They're both centered over 30,000. Now that's kind of critical. Now what we're saying, like the implication of this, is that even you had maybe drawn one sample, and it might have been randomly a weird one that oversampled really rich people or really poor people. But what we can say is that just taking a small sample and calculating the average, that procedure itself is unbiased. In other words, on average, our X bars will be correct. In other words, the expectation, so the average of all the possible X bars that we could have taken. We just have one, but we could have taken one of an infinite number of these guys. The expected value of all these X bars is 30,000. It is exactly equal to the mean of the population. And this is why statisticians are so comfortable making claims about what income is in the United States, even though they only have a sample. They feel comfortable saying that because, on average, the sampling procedure in taking averages works. On average, they're right. Now, how precise are these estimates? You really want your estimator, this idea that you're going to take a sample and take the average, that estimator, you want it to have two features. One, you want it to be unbiased, so that on average you're right, but you also want it to be precise. Right? So here's a dinky little story to kind of explain the difference. Let's say you're hunting. You go out into the woods and you're trying to hunt deer, and you see a deer, and you pull up your rifle and you close your left eye and you squint and you aim, and you miss wide left. And let's just say that the deer is too startled to move, and you have time to aim again. You never in real life do, just like you would never take two samples. But let's just play along with the story. So you pick up your rifle and you aim, and this time you close your right eye and you squint and you aim and you miss wide right. Now, you can go back to your friends and go, well, on average, I hit them. And you'd be true, like, yeah, you missed wide left once and wide right on the other, so on average you were dead center. But so what? You were wide left and wide right. Your shots were not very precise. You didn't bag the deer. So you need both things. You can't always be shooting wide left. You don't want to be a biased shot. So you'd like at least to be aiming in the general direction of the deer on average, but you also want your estimates to be fairly precise. Now we can see that here on this graph too. Not only is the distribution of X bars centered appropriately over the true population mean, but notice that the distribution here is much tighter than the distribution up here. In other words, the distribution of sample averages is smaller than the parent distribution that this thing came from. In fact, there's going to be a very precise relationship between the standard deviation of this guy and the standard deviation of this guy. Okay. The standard deviation of this second distribution, it's still a standard deviation, but we're going to start calling it the standard error, SE. And it turns out that the standard distribution of this guy is related to the standard deviation of the parent population in this way. Right? The standard deviation of the child population is equal to the standard deviation of the parent population, this guy up here, divided by the square root of the sample size. So if we had taken a sample of 100 people, then square root of 100 is 10, and so the standard deviation of this distribution is going to be this guy divided by 10. It's going to be much narrower, which means that your sample averages are very precise. Now this should be actually a little bit obvious. If all you had taken was one person out of here, man, it could be all over the place. It's got a big standard deviation. But you didn't take a sample of one person, you took a sample of 100. And so you're going to get a much more precise estimate. The larger that your sample size is, the more precise, because you're dividing by a bigger number. So if you took a sample of 1,000, then this guy would shrink, and it would be like this. And if you took 1,000,000, it would be like, whoa, it's way up there, right? So it would be really condensed like this, and eventually it's going to collapse, and you get like one number and no variation at all. Now, I have an assumption here that this guy came from a normal distribution. This guy certainly looks normal. We need to talk a little bit more about when this guy is going to look normal. Okay, so I've pulled up some statistical software, and I'd like to try sampling from all kinds of different parent populations to see what the child population will look like. In fact, that child population is the distribution of X bars, and we call that the sampling distribution. So here I've got a distribution, a parent distribution, and this one is not normal, right? So I'm sampling from a uniform distribution. Now what I'm going to do is reach into this distribution, right, and pull out a sample. That sample is going to have a sample size of 1,000. So a very healthy sample. But I'm going to do that not just once. I'm going to do it and then record the sample average. And then I'm going to do it again and record a new sample average. And then I'll do it again and again and again. In fact, I'm going to do this 10,000 times. And then I want to look at the distribution of all those possible sample averages that I might have taken from here. So let's do that right now and see what happens. So the simulation is working. It's sampling all these different sample averages. Okay, and so again, out of this parent population, I drew, how many was it? It was 10,000 sample averages, and then I drew the histogram of those sample averages of the X bars. Notice that it is right over the mean. So the sample average is an unbiased estimate of the population average. And notice how much tighter this guy is. Right? All of our sample average values are right around what the population average is. The idea behind that is that when you take a sample, especially a large sample, it's really unlikely that you only sample from the tails. So sometimes you get a bunch of people on this tail, but they'll be offset by a bunch of people on this tail. And when you average them, you get a number in the center. So it's no wonder that the standard deviation of the child population, of standard deviation of x bar, that standard error, is much smaller than the standard deviation of the population. Notice also that this thing is a completely different shape. The shape here is normal. That's going to come up a whole bunch. Now let's do another simulation just to kind of get used to the idea of the distribution of sample averages. So this time I've got a parent population that's way skewed. The average seems to be around, what is that, like 0.65 or something? Yeah, 0.665. Now, I'm much more likely to pull people from here than I am to pull people from here. But let's see how the sample average works. So I run my simulation. I'm drawing 10,000 sample averages, each of size 1,000. My distribution of x bars is again right on track. So it's collapsing around that sample average. So the range of all the possible sample averages we could have taken, at least it's on average correct. And notice how tight that distribution is. Right? That's standard deviation of this guy, what we call the standard error. It's really small. In fact, it's the square root of 1,000 times smaller. Notice also this particular shape. It's normal. Let's do it again. So now my parent population is this weird looking fella. It's got a particular mean. But even though the underlying population is seriously skewed, the distribution of sample averages is normal. It's got a much smaller variance, and it is unbiased. We can keep doing this. Here we're going to draw from a normal. That's kind of a best case scenario. And we're going to draw small samples of size 10. So just 10 people out of this population. But I'm going to repeat that process 10,000 times and then look at the histogram of sample averages. This guy is again normal, it's unbiased, and it's got a tighter standard deviation. Now what if we have a very weird distribution? Okay, so this time we're going to sample from a parent population that's really wonky. It either takes on this value, which is -0.5, or I guess it was 9.5. So it's binary, and it's very weird. It's not continuously distributed. It's seriously skewed, right? So that the average is, well, the average is exactly 0. But this is the much more likely option. All right, now what if we take a sample from this parent population, and let's have it be a relatively small sample. Let's say a sample of 30. All right, so we draw one sample of 30, we record the sample average. Somebody else draws a sample of 30, we record that sample average. And we do that 10,000 times, and then we draw the histogram of all those sample averages. What would that look like? So we run 10,000 simulations of this. Now we went from having a binary distribution to something that's still discrete, but we're starting to fill in some blanks here. The green line is what a normal distribution looks like, and we can see that we're not quite there yet. We're starting to see a little bit of that classic bell-shaped curve. The probabilities aren't quite normal yet. So here we've got a distribution that's so bizarre. It's binary, it's not continuous, it's very skewed, and we took a small sample of only 30 people, the sampling distribution is starting to tend towards something that's a little normal. So yeah, if you're sampling from a weird distribution and you got a small sample size like 30, that's not great. What if we had 300? Let's do this all over again. So we draw 10,000 sample averages, and we're going to graph those. Now, hey, that's looking normal. It's not exactly normal. That green line right there is what a normal would look like. We can see that we got a few more observations in the dead center than we would like. But man, this is looking normal. Looking nothing like the parent population, because we're not sampling X's anymore. We're looking at the distribution of sample averages, of X bars. And if, just for the sake of fun, we draw 3,000, not 3,000 observations, we take a sample of 3,000 people, and then we do that repeatedly. What would that look like? Relatively normal, unbiased, and notice that the distribution of X bars is collapsing around the population average. So our estimates of what the population average might be are becoming increasingly more precise whenever you take a larger sample, which is kind of a no-brainer, but it needs to be said. Again, it's also getting more and more normal. Let's do one final example. So here I'm drawing from another relatively wonky parent distribution. But when I calculate an average here, I've got samples of size 100. And then we recorded X bar. And then somebody else took a sample of 100. And they recorded their X bar. And then someone else took a sample of 100 and recorded their X bar. And we did that 10,000 times. This is the distribution of X bars. It is dead solid normal. It is unbiased. And it's really precise because we had a sample of 100. So the square root of 100 is 10. And so the standard deviation of this guy is equal to the standard deviation of this guy, but you're dividing by 10. So it's 10 times more precise, let's say. So in general, how precise are our estimates? We saw that it depended on two things. It depended on how precise the parent population was. So if you're drawing from a population that has tons of billionaires and tons of homeless people, then you're not going to get a very precise sample estimate. So even if you draw 20 people, you could have some billionaires, you could have some homeless, and the sample average that you would compute, it could be kind of all over the place. It also depends on how large of a sample that you take. So if you only take a sample of 20 folks, that's not great. 30 actually is a really good number. You wouldn't think it'd make that much difference, but 30 is decent. And 100, you're looking great. We saw that with our totally wonky Bernoulli distribution, that bimodal one, the one that just had two values, it took about 300. But by 300, which frankly is not that much, you normally sample thousands, the distribution of possible guesses that we might have had was unbiased. It was fairly precise. It was normal. It has everything that we want. So again, this is why statisticians really dig the sample average. It's unbiased and it's fairly precise when you've got decent sample sizes. Now this brings up an idea that is absolutely critical to modern statistics, and that's called the Central Limit Theorem. Now, what does this mean? Actually, I've been showing you with all these simulations. It's saying that for any population, right, that's not completely wonky, so you've seen a whole bunch of, I think, fairly wonky ones, but if you have any parent population and you take a sample of size little n from there, the distribution of all the possible sample averages you could have gotten will be normal. It'll have a mean that's equal to the mean of the parent population, so it's unbiased, and it's going to be precise. It's going to be smaller by a factor of 1 over the square root of n. It's going to be more precise than the parent population. Now this is true only under some conditions. What are those conditions? These conditions. If the parent population is itself normal, then it doesn't matter how big your sample size is, the distribution of x bars will also be normal. If the parent population is not normal, and we just saw a whole bunch of simulated examples where they weren't normal. We had Bernoulli, we had binomial, we had Poisson, we had a whole bunch of different stuff. Then the critical part is how big is the sample size and how wonky was the parent population. If the parent population is roughly bell-shaped, you're golden. If it's not roughly bell-shaped, then your sample size needs to be large enough. In practice, if you've got a continuous distribution, 30 is your golden number. A sample size of 30, and you can basically presume that sample averages come from a normal distribution. If it's very wonky, like that bimodal one, that the one that just had 2 possibilities, that one we saw that it took something closer to 300 observations. We have a central limit theorem that says no matter what the parent population is, if you draw a sample size that's large enough, the distribution of sample means will be normal, it'll be unbiased, and it'll have a standard deviation that's equal to the parent population's standard deviation, but you're going to divide it by the square root of n. So it's going to be more precise. Now finally, how can we convey the amount of precision or imprecision? In the next video, we're going to talk about constructing confidence intervals. Now what that means is, I want to know what the sample income is in the United States, and you draw a sample and you say, I think it's 25,000. But now we want to convey the imprecision, and we can do that by either saying what the standard deviation is, your standard error, because you're talking about averages, or you could just give me like a range of plausible estimates. You could say something like, I think it's 25,000, but it could be between 24 and 26. Or it can be 25,000 plus or minus 2,000, plus or minus some standard error. Plus or minus, well, some number of standard errors. So next time that we meet, we're going to talk about conveying imprecision using interval estimates rather than one particular point estimate. All right, thanks for listening.